So, hi. I'm very glad that I have the opportunity to speak about that stuff here. I'm Oliver, as I said. That is the link to the slides. I will post that on Twitter as well. So, this is about machine learning, and when I prepared the talk, I tried to understand what you already know. I got 19 votes, so I have to repeat that. Who has no idea about machine learning? Maybe a third, maybe a fourth. Who knows the basic? That is maybe, that's less. And who actually knows a lot about machine learning? A few people. That makes me quite happy, actually, because that talk is for beginners. So I have a lot of pictures, but unfortunately I have no cats. And I have no badges, but bear with me, I'm sorry. Okay, because there may be some people who have no idea about machine learning, quick introduction. So machine learning is about making machines act without writing programs. So, well, and that's an example that I actually took from somewhere else, and that example is to tell an orange from an apple. And you may say, that's pretty simple, you check the color. And the orange obviously is orange. Even though I recently read that some oranges actually are green, and they are still okay, but in this case, you might check the color, and you say, okay, I check the color value of my image, and then if it's mostly orange, it's probably an orange. But then, what about black and white pictures? You can still see that the thing on the right side is still an orange, but it's not orange. So, what about things that are neither an orange nor an apple? So, like a banana. What do you do about it? So, how do you learn it? And then, typically, you can write a rule for each of these things by hand. But what you tend to do then is you forgot at least one, and sometimes you overspecify. So you're too strict. Maybe you have one rule too many. So, and instead, you rather let the machine learn for you. You let the machine learn the rules. And there are different technologies to do that, but basically you feed in examples, and from those examples, you make the machine learn. That's machine learning. And where's that useful? Something that really struck me and that I like a lot. So actually people begin to build in a special kind of neural network into ultrasound machines to detect cancer. So there might be a certain pattern, and if the machine recognizes it, it tells the doctor or whoever, that person, that patient may have cancer, which is automated. Pretty cool. And then stuff you probably saw before, that is like making machines learn to drive cars. I think there has been an incident yesterday that might question this, but that's possible. And I have some rubber duckies, at least. No cats, but duckies. And then it's hard to see, but this is actually space invaders played by a machine. And why that is important, we will see a little bit later. There's something else that is also probably a little bit too small to see. That is movie scenes, and a machine learns to predict what happens next. If they kiss, if they hug, if they fight, and they're doing fairly well. Then there's something that's a little bit more boring, just to find out where's the number plate and what's on it on a moving thing, and then eventually playing games like Go. Who has followed the AlphaGo versus Lisa Doll thing? Oh, that is a low percentage. So recently, a machine beat the number 2 in the world playing Go, and that was something that was thought to be impossible for a machine. Because the way machines play chess, for example, is very different, and playing chess is solvable by a machine, and you can beat humans, but Go is much more complicated. So no one thought that would be possible. Now AlphaGo, a machine is actually, I think, number 2 in the world range. So machine is number 2 in the well, I don't know, in the high score thing. Okay, those are applications. So now, what does this have to do with us? So this is about machine learning and in the browser. And Google recently released a set of tools, libraries, and among that is a playground that lets you play around with machine learning things. I added a link, and I will lead you through this as a first introduction, and I'm going into it in a second. I think it's pretty bright in here, so I hope you can see all that. I think it's okay. So first of all, I prepared an example which is almost built into that TensorFlow Playground. As I said, it runs in the browser, and that is a classification problem. That is very, very common for machine learning. So what you want is to make the machine distinguish between 1, 2, 3, 5, how many sets, whatever, so that the machine can tell you, is this or is it that? And in this case, as you can see in the lower left, it distinguishes between blue points and orange points. So those points, they are in a plane, like in an area, as you can see, and the background color actually is a prediction. If there would be another point, would it be either would it be either blue or orange? So the background color is the prediction. And as you can see on the right side, the algorithm that's used, that's called Softmax, it doesn't tell you, I'm very sure that's 100% orange or 100% blue, but it rather tells you in a range from 0 to 1. So if something is dark blue, it's very likely that it is blue. And if it's in the middle here, that is around 0, so it's very uncertain what it should be. But as I said, the background of the whole thing is actually the result of a learning process, of a prediction. And I'm going into it in a second. What I also said is that the prediction that is being made, it's learned. So you feed in certain points and tell the machine, okay, this blue spot is at this position, so it should be blue. So you do this for several times, and then eventually you have it trained. And I will show you this live in a second, if the network works for me. Okay. So how does this work? So this is a certain kind of machine learning. It's using neural networks. So it's just one technology, but it's the most interesting and the most groundbreaking technology right now. And on the right side, you see a single simulated neuron. Sometimes it's called a perceptron. It doesn't matter much. It's mathematics, more or less. So what you have on the left side of the right side here, you have inputs. And those inputs, they are weighted. They have weights. So you have input x1 to, I don't know, n. And you have weights, and then you multiply each input with a weight, so that input is numeric, and then you sum it up, and then you have an activation function, which can have many shapes, but it doesn't matter a lot which shape it has. Not for us. It's rather a detail. So it's typically an activation function that looks like a sigmoid. I should have an image here, but I don't have. It looks like this. Or like this. So it typically starts in the negative or in 0, and then certainly goes up. So from that you compute an output, but you typically just don't have one neuron, but you have a lot of neurons. And on that left side, I have a configuration of neurons. And this is what I'm going to show you live. I hope it works. It works, great. So this is the playground, the TensorFlow Playground, done by Google. It's written in TypeScript. It's compiled to just run in the browser, which is nice because you can just experiment without installing anything. This is just, you see, this is just Chrome. So what I have here, I have a configuration of a network. This is just one layer. I'm going into it in a second. And this is one neuron, this is one, and this is one. And those are the inputs. Hope you can see it from the back, and they are weighted. And the bigger they are, like the stronger they appear, the more weight they have. This is the prediction on the right side, and as you can see, do you think that's a good prediction right now? If something is a blue or an orange spot, is it a good prediction? Who thinks it's a good prediction? Okay, two-person thinks. But it's actually not a very good prediction, because this says this is blue as a prediction, but obviously those points there are orange. And it is a bad prediction right now because that network is not trained. And that means those values on the weights here, they're just random. But what I can do now, I can make this run, and my machine gets hot now, like really hot. And what it does, it goes through a lot of iterations. Look at the right over here. those values change, and you also see the graph, and that tells me how well the network performs. And I have two values, and I'm going into it why I have two values, but that's what it does, and I can stop it now. And you see that now it predicts fairly well. So it says every spot that's in here is probably blue, and every spot in here it's probably orange. And I can see, by going over those neurons, what they actually contribute to the overall result. And as you may see, and if you're very good at mathematics, you probably already figured that out, each neuron can separate the plane using a line. That's what they did. But if you combine all that, like 3 lines, you get a shape like this, like the eventual thing. First line, second line, third line, hopefully you can see that. And we actually trained the network to predict very accurately what point would be a blue line and what would be an orange line. Just to show you something, I can add neurons here just on the fly. Obviously, my network was powerful enough to do the job. I can add more neurons and start training. You see the shape changes now. It's no longer a triangle, but it gets rounder because now you have more lines to add together. And then it doesn't get any better because the prediction already was very good, and it takes a lot more time to train. And you can also add layers. So this is one layer. All the neurons, they get the same input. And I can add a second layer. And add a lot of neurons, and now I train. And it again gets slower, and my machine again gets very hot, because that is very, very computation intensive. But you still see that is a very easy problem to solve, because all the configurations that I just showed you, they could actually give a very decent prediction. Removing one layer. What do you think? I mean, how many neurons will I actually need to get a very good prediction? How many? I heard 2. Let's try that. Oh, you see 2 lines. It's trying very, very hard, but I can tell you that whatever you do using 2 lines with this thing, you won't get a good prediction, because in whichever way you draw 2 lines, you can't like wrap the circle in the middle. So it won't work. You just have to trust me on this, but so proving that something doesn't work is always very hard, so we have to wait for very long, and I'm running out of battery already. So it's not enough. So you need 3 of them, and then it will work fairly quickly. But we get back to this, because that is one of the key problems of machine learning. How many neurons you need, how many layers. That's pretty tricky. Okay, that was just an introduction. I should be halfway through. I am, which makes me happy. Oh, sorry. There we are. Okay, so what I showed you, how does a neuron work and how do you put them together into networks? Okay, now for the JavaScript. So this was one library, one very new thing, TensorFlow, and this other library, it's comparably old, so it's 2 years old, I think. It's done of one of the most influential developers at Stanford. It's called ConfNet.js. And I'm just opening it here. It looks a little bit less beautiful. It looks like an UI I would have done. But it has the benefit that you just write, I'm zooming in here, that you can just write JavaScript to configure your neural network, and you can try out a lot of things. So while the first thing, the TensorFlow thing, is great, just try things out without programming, you can directly enter JavaScript here. I will show this. I'm zooming out because I need to see things. It's a very similar problem. This time we have green and red dots, but other than that, it's the same classification problem, exactly. And I can actually manually tweak this, and it learns on the fly. Now I make it very difficult for the whole thing. You see, it's very hard, but it learns. But look at the configuration of the whole thing. I think you can already understand what is here. So those are the interesting parts. This is the definition of one layer, and I have 6 neurons. That is the activation function that you can just ignore for now. And I have a second layer, and it has 2 neurons. And let's see how it is doing. It's doing fairly well. You see fairly complicated shapes here, but I can change that back, remove one layer, and that makes it really fun, because I can do this in the browser, or I can write a program that does this, and I'm restricting this to 3 neurons because I know it works. I'm just changing it, and on the fly, the network configuration is changed, and then you see it's doing okay. So same thing. I'm showing you this to show you this all is possible in JavaScript. This is just JavaScript. It's no additional library, no Python, no C++. Going back to slides. I'm showing code now. I think you can read that well. I think I did good. I removed the colors from the code. That is the code that I already showed you. That is the code that you changed in the browser. And what you do is you specify an input layer. It's all neurons. Then you connect each input to the first layer, which is in line 3, having 6 neurons. Then line 4, second layer. Again, each output of the first layer is connected to the to each neuron in the second layer. And because of this, it's called fully connected, because it is fully connected. And that is the abbreviation. You know what I mean. So this is like the abbreviation. I need to drink something, I think. Give me a second. Abbreviation, now it works, of fully connected, and eventually put it into the last layer, which is called Softmax, which more or less like tries to find out which of the two classes actually can be predicted. And that I have 2 classes I put in here. So this is just JavaScript. It uses that library, fair enough. And eventually use a trainer to train it to do the right thing. I'm coming to the trainer in a second. Okay, under the hood, just to give you an idea that this is not magic, I just copy-paste some of the code that the library actually uses, and it works like this. You create a point in line 1 and 2. It's a strange API, so don't bother with the details. And then what you do, you have the network here, and you feed it forward into the net. That means you put in that point, this one, you feed it in the net, and it returns a prediction for you. And the prediction is between what is it? Yes, the prediction is actually, in this case, it's a two-dimensional, it's a vector having 2 values, and the first thing tells you what is the probability of this thing being in class 0, and what is the probability of this thing being class 1. And if class 0 is bigger than class 1, then it's red or orange, and otherwise it's green or blue. That's how you make a prediction. That's all very, very simple. So if you're looking for the hard parts, there are none. Not for you as someone who uses it. And then those predictions, they get painted as a background color. It's very easy. So coming to the harder part, I said I have 2 values here, this thing. It was test loss and training loss. Any idea what that could be? Just to, why 2 values? So to give you a hint, people and I typically spread the set of data that you have into training data and test data. So with the training data, I train that net, and then with the test data, which has not been used to train the net, I check the net. Why would I do this? What could it be good for? Anyone? Yeah? To see if you have learned the right thing? Yes, to see if I've learned the right thing, exactly. So you have those 2 sets, and you have like a quality measurement for 2 sets of data points, and the quality measurement for the training loss is very close to 0, which is good, like 0 is perfect, and the test loss is also very close to 0, but a little bit less good. And this is done to prevent so-called overfitting. Overfitting means you just perfectly mimic those data points that you used to train, but if you have this, you forget what all this is good for, to predict something that you've never seen. So you want to be a little bit more general. So you split your data set into things you use for training and things you use for testing. And if they're close to each other and close to 0, you did good. If the training value is close to 0, but the test value is very high, like 0.5, which is just random, then you did bit bad because you overfit it. In this case here, the things that are surrounded by white border are, let me see, white border is training, black border is testing. So I split 50-50, but in the TensorFlow Playground you can just choose. Okay, I was talking about training, and I have to speed up a little bit, but only a little bit. How does it work? How do you train? I showed you how you predict. Now I'm showing you a little bit of JavaScript code. It's a little bit simplified, but not really. And I'm putting it here to give you an idea how simple it is to write something like training. Okay, what do you have in line 2? We have all the data points that I use for training. So those are coordinates. And in line 4, I have the labels. So the first thing, this thing, it gets a label 1. This gets a label 1, and this gets a label 0. And this is for training. So this is what I know. And now I'm iterating over it for many times, and you already saw iterations. Let me change to this. Here you see the number of iterations that I did to train the network. Those were 400 iterations. In this code, I have chosen, I don't know, 20 iterations, and I go through all the data points. I create the point, I create the associated label, and then that's the important line in line 12. I put it into a trainer, and then I say, for this point, please learn this label. And I repeat, and I collect the loss and divide it by the number of iterations, and then I have that, what you see up here, this thing. That's the loss. Okay, it's very easy. And by doing this, by having a trainer like this, you turn this whole training thing into a numerical optimization problem. And ConvNet, the stuff that you saw, it uses stochastic gradient descent. And the good thing about this is you don't have to understand how it works, because it just does it for you. Well, I try to understand it. It's tough, but it's possible. But as I said, you don't need to understand it, because it typically gives pretty good results. So that's a mathematical problem. Okay, that's more or less for just normal networks. And if you think it's all very simple, it is. You need to understand the basic, play a little bit around with the TensorFlow Playground. What is hard now is how do you actually configure a network like this? You played around with a network, and you try to guess how many layers do we need, how many neurons in that layer. And so the bad thing about this is no one knows how to actually configure stuff for a given problem. So everyone tries it out. Or if you actually can fall back to expert, you use pre-trained networks. And that's what the automobile industry, for example, do. They buy pre-trained network data, maybe from NVIDIA or some people, and then they put it into their chips. And probably many of you have cars that can detect traffic signs, like speed limit signs. Who has a car who can detect speed limit signs? Oh, okay, just 2. But I don't have one either, but I know they're around, and I also know that low-cost cars from Italy will next year have this. I can't tell you more. But they do it by trained networks. So if your car can do it, it's probably premium. But it's done using neural networks that have been pre-trained. And as a side note, the operations to actually make a neural network work, to make a prediction, are matrix multiplications, which by incident are what graphic cards, for example, from NVIDIA, are very good at. So the good thing is we have specialized hardware for a very low cost, because who's a gamer here? Who likes to play games? Okay, it's your money that actually propelled the neural network thing, because the GPUs are very good at that. Okay, just as a side note. Okay, what else? That was a little bit JavaScript. What else is possible? Just a very brief overview. Those neural networks, they can also process images. And the graphic on the bottom, it tells you a little bit, like very very abstract. It tells you a little bit how that works. You put in an image, and you have a lot of layers, which are also neural networks, and each layer provides a number of filtered outputs. If you've ever done graphic processing and know what a filter does to an image, that's exactly that. Just that is done by a neural network that is able to learn how to filter. So you take one image, you filter it using 1632 filters. That is the new input to the next thing. Then you make it location invariant, and eventually you have something that has a lot of semantic inside, but very low resolution. And because it's impossible to explain that in just a few minutes, I actually found this on the internet, again, which gives you an intuition. So on the top, I have dogs. I don't have cats, as I said, but I have dogs, and they're pretty cute, I think, I hope. But they're also pretty similar. So my task now is to learn from those pictures. Better to say, the machine learns from those pictures and tries to find an abstraction. And someone did a great job by providing this. So this is actually a graphic representation of what the machine learns from those pictures. And that's quite funny, isn't it? So it's reduced to the snout and the eyes. And if you look at those dogs, that makes sense. I mean, if you had a pug in it or another kind of dog, it would be wrong. But given those pictures, this is what a neural network can learn. And now you see this dog up here. It's a little bit moved to the right. So those networks, they can not only like abstract from features, but they can move things around. So it doesn't matter much where the thing is in the picture. This is done. You can do this in the browser this afternoon if you want to, because it's very easy. It's very accessible. And as I said, one application is detecting cancer in ultrasonic, I don't know, ultrasonic machines. Okay, coming to an end now. So the other thing that maybe has less applications, but is still very interesting, is you can train networks by making it play against itself. And they did it to create a machine that is very, very good at playing Go, like playing against Lee Sedol and beating him. And they also used those networks to directly learn how to play Atari games. And they often outperform humans. Okay, I'm almost done, so I have to skip this slide, unfortunately. Just wrap it up. So those deep neural networks, they actually are a game changer. So that wasn't what you can do now was not possible a few years ago. And is now possible because we have large data sets. We have a lot of data we can learn from. We have computing power, and we have very powerful GPUs. Okay, and if you want to try that out, you can just do it without installing anything. And you can use it in the browser, and you can also like couple it with visualization, which makes it much more like understandable. And it's very good to learn something. Okay, that's it. Thanks a lot.